Hey folks, so in this video we're going to introduce the idea of hash tables and use them to implement symbol tables. Now in previous modules we basically had all these other different implementations that we could possibly have for symbol tables. Now the last one we had that had pretty good performance was having the idea of a binary search tree. And so our overall goal, right, is basically to implement this ADT, which we call the symbol table, which had all these key value pairs being stored into it. And initially, right, we start with something really simple, a list, an array, and those things end up being a little bit slow, and so we try to get faster and faster and faster. And so we went, right, and we did binary search trees, and binary search trees did a pretty decent job. The performance we get out of a binary search tree looks something like this, big O of log n. That's, it's pretty good. In practice, I guess you could have, or okay, not in practice, but I guess to be more specific, right, we could even say this is tilde of something, and I forgot the constant, but it's like 1.6 something of log n, right? And I mean, it's not bad, right? It's not bad. It's log and log, right? I mean, that's okay. But we'd like to get better, right? We always want to get better. What is as fast as we can do? The only thing really left for us, right, is to go to constant time. And so in this kind of module content, that's what we're going to be doing. Our new idea here for this concept of hash tables is actually going to let us get to this constant time, right? And at that point, basically, we can call it a day, right? I mean, you can't really do better than constant time. All right, so how do we get there? How might we get a lookup structure, right, the symbol table? How can we implement it in this O of one time? What could we do? Well, the first thing is, right, and this is kind of we're forced to do this, we have to go back to arrays. Because the problem is, the only data structure that I have that has multiple elements in it that I can access everything in O of one time is an array, right? If you think about a list is going to cost you, right, to get to any element in there. The only thing we know about, right, that can really get us constant time is an array. So we're back to arrays. We're kind of, going full circle, right? We started by saying, oh, arrays are cool, but we want to make them more general, right? We can extend them. Now we're all of a sudden saying we're going back to arrays because they are indeed the fastest things that are out there. What are we supposed to do? Well, here basically the problem is the following. We need to take our little keys, right? So we've been having this generic idea of a key, right? Something like, for example, well, in an array, right, it would have been a number. We wanted to make it more general, right? Something like a string, right, or object, or whatever you want. Take a key and basically convert it into an index, right? That's kind of our overall want. And so what we'll introduce here is basically this idea of a hash function, right? Obviously, right, the reason we need a number is because arrays are indexed on numbers, and so I need to have some sort of a number associated with each key, otherwise I can't hope to put it in that array. So the terminology we'll have here, right, is basically of a hash function. So a hash function is basically going to be this function that I have, I basically put in an object, or I put in a piece of data, and it gives me back a magic number, right? I put in a key, and I get back this number that encodes the identity of this object, right? So it's like all of a sudden I'm converting anything, right, into a number, right? So it's as if I have some way to do like something like this. Like, so I could have, for example, go for the word cat again, and this, right, somehow gets converted into the magic number 15, right? I want some way to basically convert any type of data into a number. Or maybe I have something that's like the current date. So like, let's see, 0808. I think, no, today's the 10th, but we'll go ahead and put in the 8th, because then it'll give us a cool looking number. 2018, right? So maybe I have some sort of a date like that. That's, compound data type. But I should have, right, some hash function that I can take that and basically get another magic number for it, right? This is maybe 277. I don't know. I'm just making up stuff here. Somehow, right, the idea is we put data in, we get a number back out. So maybe if I were to diagram this a little bit up top, I want to have basically an object, right, which is really a key, right, for this situation. And I basically have, this thing over here, this arrow, right, which is a hash function, right? This is basically what's doing the transformation, hash function. And this gets me an integer, right? That's what I want to produce. So I'm trying basically to flatten everything into a number. Because once I have an integer for every single key that I could possibly store, that number somehow I could think about using it as an index into an array. Now I'm going to do a little bit of work, but I could do it, right? I could use it basically as an array index. And if I were to do that, all of a sudden I get constant time lookups, right? So it's like, well, I want to know what is the, the value associated with the key cat. Well, what I would do is I would basically take cat, put in this hash function, get the number, and then use a number to look up into a specific entry within that array, right? And that lookup operation there at the very end, that's going to be constant time for sure. Assuming our hash function is constant time as well, the whole thing is constant time. And so, hey, we have constant time lookups for a symbol table. Very nice, very nice. But it'll be hard, okay? It will be hard, okay? This is the hope and the dream, but it's not quite what we're going to have. The first thing that gives us trouble, right, is the construction of hash functions, right? That's going to be a little bit problematic. Also, what's going to be problematic is basically handling that array behind the scenes, right? Because we're saying that, oh, to get constant time, we basically need to throw everything in an array anyways. Handling that array will be costly as well, because you do have to worry a little bit about things like resize operations, or actually what we'll spend the most time on is something called collision resolution, which is actually sort of like the central theme that we'll move towards in this series of videos. All right, so a few other things to talk about here. So some more about hash functions. Just here what I want to do is introduce some terminology or some common variables that we have. The first thing here is that we say we're basically going to be storing our data into some array that has m indices. So m is the size of our array. When we talk about the number of elements, we'll use the number n, right? So there are n elements in an m-size array, right? Those are two things: n elements, m indices, okay? All right. This over here, right, is kind of our main rule. When we talk about hash functions, right, when we talk about basically producing a hash, right? So on the previous slide, I written up here, object goes to int, right? This int somehow over here, right? This is a hash value. It's a hash value produced by a hash function. All right. So our hash, right, should basically encode the identity of a key. And so what do I mean by that? On the previous slide, I had, for example, this over here. I had, and I'll start at the top so I have space to work on. So I had cat. I can spell. I can't even write here. Let's try this again. So I have, cat. And I said that would maybe hash to 15. Great. Now, this is kind of the key thing here, is if I change anything in my key, right, here it's a string, I should change the value of the hash, right? Because that hash is encoding the identity of the key. So if I have over here cat exclamation point, I would maybe get something like 281, something like that, or 2,801. Completely different, right? The number doesn't even look the same, right? So sometimes, right, when people see this for the first time, they think, oh, I'm going to add something to the hash. So that maybe means that, cat exclamation point should really be like 15.1 or something like that. No, the numbers here should be completely distinct. We basically want to have, this magic number, right, that basically just encodes the identity of just this, of whatever it is I'm using as my key, right? Okay, so I can put anything else in there, right? And hopefully, get a different value. Well, I need to get a different value, otherwise it's a bad hash and things will, not work out for us. So any change, I give a different value. Also note, that something we want to avoid, and this is what we're going to try not to do, right? We're going to try very hard not to do it, is have issues like this. So let's say we have this. So we have SER222 is having that hash to the same number, right? That would be very, very bad. That doesn't make, so conceptually it shouldn't make any sense because, hey, our hash is a number that's supposed to encode the identity of a key. So if I have two keys that are different, right, and cat exclamation mark and SER222 are clearly different strings, right, and we're treating those as keys, they cannot be allowed, right, to map to the same number, right, because that number is supposed to encode identity, and so all of a sudden that number really doesn't mean anything. It's like it was arbitrarily picked, okay? So that, doesn't make any sense here. Now, if I were to take a key and maybe hash it again, right, independently, right, run it through this function again, I should also get back the same value, right? This is the second thing we expect to see, right? So if I hash cat again, I get back 15. Anytime I hash that particular key, right, that's the same, I should get the same, magic number back. I shouldn't get anything else from it. I need to get that same thing. All right, so hash should encode the identity of a key, okay? All right, next thing. So when we produce our hashes, we're eventually, right, and this is going to take a little bit of work, wanting to basically map to this range. So 0 to m minus 1. Because we're saying we're storing in an m-size array, we need to basically, be generating hashes that fit in there somehow, right? I don't want to, end up having a hash that's too big for my array. That would be trouble. Now, this is something that we're going to spend, well, it's going to be a little problematic because what's going to end up happening is that when we write hash functions in general, we're going to make sure they basically can, give any possible number, and then later on we'll shrink it down to fit into the actual size of the array. Because hash numbers, right, or hash values, I should say, basically they're meant to encode the identity of something. I basically need to be able to have any number there, right? Because m could be something really small. If m is something like 10, then it's like 0, 1. I don't have many choices of what I could number something, right? I end up with this case over here where we had collisions. That was bad. And so initially, kind of when we produce hash values, there'll be kind of any number possible. And then later on, right, in order to store them actually into this array, then we have to confine them to this interval, which is 0 to m minus 1. All right. So that's kind of our first note there. Our second note is we want to produce hashes that are uniformly distributed. So somehow what we're saying, right, is we have this interval here. And when I create hashes, I should get a number over here, a number over here, a number over here, number over here, number over here, number over here. Something like this, right? Like a pattern like that. What I don't want is this. Get everything in the same spot. This is just bad, right? Because what happens is you end up basically with a lot of kind of collisions here, and you have a lot of things that somehow have this thing going on, right? And we don't ideally, right, we don't want that at all. But as we make, as we make m smaller, the chance that happens increases. the chance that, and then also, right, if we're not uniformly distributed, that chance that occurs also increases. So it's a bad thing, right? We want to keep this, kind of evenly spread out to maximize the usage of our array that we'll have to construct at some point to store things. All right, so there's a bit of a trade-off here, right? So we could actually think about making, m super large relative to n, or n super large relative to m, right? We could think about making one larger than the other. Now, if we make m really large, which is the size of the array, well, what's going to happen is we're going to have a very, very low chance for collisions, right? We're going to basically get, this O of 1 access time, right? We'll basically just be able to jump, to any possible thing. It'll be really straightforward, really fast, okay? But that's provided that I make m really large, right? Because if m's really large, nobody ever hits anybody else. Basically, whatever hash number I generate, I can use it directly as a key. No need to play with it or mess with it at all. Things are fast, but then I've spent a lot of space on that, that data structure. I've had to allocate this huge array with billions of spaces. That's maybe not something I want to do, but it's just too expensive in terms of performance. The other option, right, is maybe with the n value, right? So that n value, I can make it really large, right? Maybe relative to m. But what happens is now I've minimized my usage of space a little bit. But instead, it's like, well, if I have a very small array, I'm going to end up with basically everything is colliding. Right? Everything wants to be stored in that same position in the array, and that's going to get me into trouble. And one way we kind of resolve collisions is by saying, oh, maybe I can have this bucket here, and I'll throw everything in the bucket, right, that has that same number on it. And then when I want to go retrieve something, I'll have to go through that bucket and see which is the thing I really meant. The problem is that's kind of going to be like one of those O of n operations, because all of a sudden we have to go inside that bucket and search through everything one at a time, right? So that's going to be very expensive. So if I kind of raise one of these too high, right, n or m too high, then it's going to be bad, right? I'm going to either spend too much time or spend too much space. In general, what you kind of aim for, as just kind of a general rule, is for n basically to be, well, n should be basically half of m, is basically the rule, right? So it's like if we have this array, I want it half to be full, right? That's kind of what we want. So yeah, that's kind of how we talk about things, right? Talk about in terms of m and talks about in terms of m. These are basically the ways that we describe kind of the scale of our arrays, right? And we talked about, right, basically this idea of a hash function and how we take, data and basically convert it right into this special identifier, right? And we're going to go through the actual code for it right now. We just have the concept of it. But, the special identifier and the special identifier, right, ends up being an index into this array. All right, so that's all I got for now. I'll see you guys in the next video.